Good afternoon, and thank you to the organizers for being able to participate in this meeting. It turns out that I may be one of the ones who was here longest ago. In fact, longer ago than Henri Aloul. I think it was in 2001 when I was last here at a high field conference. So it actually took 18 years until I was invited back. So hopefully I'll do a little better. What? 1993. Oh, wow. Okay, wow, that's okay. Sorry. okay, I just a child, yeah, but there you go. But it's always been fantastic to be here. Okay. Okay. All right. But it's been great, and I really like the kind of lively, interactive atmosphere that we've had many times. I would hopefully not degrade that by doing PowerPoints. So please, interrupt me, and we'll stop and talk about whatever you'd like. What I'd like to talk about in most of the presentation is quantum magnetism and how we use neutrons to probe it. And in some sense, I think it's pretty natural that we would be using quantum beams to probe quantum materials, and that's kind of the idea that's going to come through the talk. But since it's a school, I'm trying to give you really sort of an introduction to the way that we think about these experiments. And I'd also like to get to the point of describing some of the challenges that we are facing experimentally as we try to explore this concept of quantum spin liquids that was introduced to us by Lucy Savary. So here's the outline of the talk. And if we get through several of these things, it'll be good. The basic idea that I had was to tell you about the scattering technique, to tell you about how we use it to probe electrically insulating materials, so that there will be all insulators. We just want to think about the quantum magnetism of the localized moments in these materials. And then the idea was in the next lecture on Friday to go towards the metal insulator transition that we heard about on Monday, and then towards more strongly correlated electronic systems. But it's quite possible that we would only manage to do 1, 2, 3 today, and then we'll get into talking about the entangled quantum magnets on Friday. We'll see how it goes. So just feel free to interrupt as we go along. So first, a bit about scattering. Then I'm going to take the viewpoint that somehow we generate local spin degrees of freedom in the solid, and I want to think about what is the character of those local spin degrees of freedom before we actually let them interact with each other. So we'll use neutrons to explore the character of these local moments, and then we're going to allow them to interact with each other, and then progressively move from pretty well understood essentially magnons in various types of materials, and then towards spin systems that may be defined by their entanglement first in 1, 2, and then 3 dimensions. All right, so let's see how it all goes. I wanted to refer you to a lot of very nice books covering these kinds of topics, specifically the scattering technique. You can look at, this is my preferred initial introduction by Gordon Squires from Cambridge University. It's quite thin and really concise and nice. This one has the full story in it. It's a little heavy to digest to start off with, but it's quite good. I think it's really nice as a reference piece. And then there's some more modern books that have come out recently with additional kind of information. And I also wanted to advertise some online lectures that we recorded back in 2012, and you can actually get to them on this website. I think there are about 30 lectures or so by various people talking about the neutron scattering technique, all possible uses of it actually. Mostly in hard condensed matter physics. All right, so that's the introduction. Then I'm going to start basically from the beginning. And so we're going to be using neutrons to probe these materials. The features that I wanted to emphasize is that the neutron has no electric charge, so it's a really penetrating probe. When it sees a solid, it just sees the nuclei, essentially, and then a little bit of the magnetic field generated by electrons. But it's kind of a very strange view of matter that you get when you use neutrons to look at materials. And that's why we like them and why they're useful. This is their mass that's very important, and the specific value of the mass actually is what makes them particularly useful in condensed matter physics, because when they have the wavelength of the lattice spacing, they also have the energy of collective excitations in solids. So we can really do proper inelastic experiments where we use the neutron to excite, let's say, a phonon or a magnon or a spinon, and you'll see a lot of this during this talk. It interacts with solids through the strong nuclear force and through the electromagnetic interaction with the conduction electrons, because it carries a magnetic dipole moment and it's a spin 1/2 particle. Okay, now the actual measurement that we do is measuring a scattering cross-section. So let me just give you a few hints as what that actually means. The experiment is conducted by first preparing an incident beam of neutrons with well-defined momentum and therefore energy. So we know the direction of the neutrons. We may or may not know the spin direction. But for now, let's consider that we are not controlling the spin, but we're controlling the momentum and therefore the energy. And we can talk about the flux of neutrons, which would be the rate of neutrons passing through a certain cross-sectional area divided by that area. So this is something that has dimension of neutrons per square centimeter per second. And the typical numbers that reach the sample would be from 1 million to 1 billion neutrons per square centimeter per second. Now that sounds like somehow a relatively large number, but it's absolutely dwindling compared to anything you do with a laser or with an X-ray source. So it's a really, really low flux technique, and it will come out through the entire talk that we're always scrambling to have more neutrons and to be able to deal with the statistical error in our measurements. Good, so this is preparing the beam. And then what we're measuring is essentially something about what gets scattered from the sample. And the first question you could have is, what's the overall rate of scattering? And so that would be something about number of neutrons scattered divided by the flux, or the rate of neutrons scattered, so that's neutrons per second, divided by the flux. And that takes the form of an area, as you can see, because this thing has neutrons per area per second. So this entity has dimension of an area. So that's the overall scattering cross-section. And it turns out that the cross-section per atom, due to the strong nuclear force, ends up being in the range of Barn, which is 10 to the minus 24 centimeters squared. So this is something like the surface area of a nucleus that we would, as seen by the neutron. Okay, now this one is a little bit dull to measure because it's just some overall number. So we need to become more specific. And so what we would typically want to measure is actually a differential cross-section, which is the rate of neutrons scattered into some solid angle d omega divided by the flux and that solid angle. So that becomes the intrinsic quantity that we'd be measuring. And so that could tell us something about the structure and maybe the dynamics of the material. We could become more specific and say that I'm not only going to require the neutrons to come off in this particular direction, but I also want them to fall in some particular range of energy that I would call the final energy. And then I'd be talking about measuring the partial differential scattering cross-section. So this is d2 sigma d omega dE, the rate of neutrons into d omega and dE, divided by the flux, the solid angle, and the energy bandwidth of my detection system. So actually, for much of what I'll be talking about today, we are discussing measurement of this partial differential scattering cross-section, and we can measure it in absolute units. It's always sort of a ratio of count rates in the detector to a detector that we have here in the incident beam, and then with an overall scale factor that we can determine by having a known cross-section in here and then calibrating in that form. I should say that the way we detect neutrons, it's always a destructive method. So once we've detected it, it's gone, essentially. So the detector that we have in the incident beam, it just detects maybe 1 in a million neutrons, and then that neutron will be, in fact, gone, but it will be telling us that there was a certain flux at this particular position. So that's what we're actually measuring. How does this then relate to the properties of materials? Okay, so first we have to think a bit about how do neutrons interact with the materials, and as I mentioned, it's through the strong nuclear force and through the magnetic dipole-dipole interaction. And let me first say a few words about the interaction with the nucleus. So this is the Fermi soda potential, that we use to describe that. And you'll see that I just have a delta function sitting there. So the nucleus is described as basically S-wave scattering and localized specifically where the nucleus is. This is appropriate in this context because the nucleus has dimension of femtometer, whereas the neutron wavelength is in the angstrom range. So to the neutron, the nucleus looks like just a point. So I don't need to worry about the specific, spatial character of the nucleus, and I can just characterize all of the scattering in terms of a single length scale that I will denote by B. That will turn this Fermi-Soto potential into something of dimension energy, because this is 1 over volume times a length gives me 1 over area multiplied by this entity, and I'll get to something which has dimension of energy. This, by the way, lowercase m for us is always the mass of the neutron. Okay, so that's the strong nuclear force. Now the interesting thing is that the characteristic length that we associate with each nucleus actually varies kind of not randomly, but sort of to someone who doesn't know where it comes from, it seems to be more or less random through the periodic table. So, for example, hydrogen has a very large scattering cross-section, and then something like silicon is quite small. Iron has this size. And so this, you could say, well, that seems a little weird. Perhaps it's a little weird, but it's actually quite useful to us, because it means that as opposed to X-rays, where the cross-section just varies in proportion to the mass of the atom, actually the mass squared. In this case, we'll get kind of the ability to have contrast between iron and hydrogen, for example, in a material. So I can see really light elements inside materials that are otherwise really heavy. So to X-rays, I wouldn't be able to see, for example, oxygen in the presence of lead. That would be quite difficult to have contrast. But for neutrons, those have the same contrast, actually. And up, the question? Which one? D? Oh, deuterium. So the reason that I mentioned deuterium here is actually that different isotopes have completely different cross-sections of interaction with the neutron. And this is part of our kind of tool cabinet that we use. If we would like to change the contrast in a material, we can change the isotope on specific sites within the material to light up some parts of the hydrogen and mute other parts of it. So there are all sorts of tricks that we can play because of that. And I wanted to show you that there really is something like Neutron Vision that you get out of this, which is this strange contrast where we in fact have great sensitivity to very light elements, particularly hydrogen. It means that, for example, here I have a nozzle, and perhaps you'd like to understand whether there's a channel through it or not. With X-rays, this would just be completely opaque. But for neutrons, I think this one may be made of lead, for example, or could be steel. Then it's quite easy for me to actually see straight through it. I can see this channel passing through because the interaction is overall pretty weak. So I get kind of a strange form of contrast. Here's another case, the poor wasp. Eventually it flew off and it was happy and so on. But we took a picture, with regular light, and it's caught in tweezers here. Here is then the image with neutrons. And you can see that the wasp shows up sort of, you can get beautiful contrast, and it has kind of the same level of contrast as the tweezers themselves. So even though this is steel, which is much, much higher density than the wasp, then the neutron basically has excellent contrast even with this very, very light material. So that's actually used in many different contexts. For example, it's possible to make a movie of the oil passing through an operating engine using neutron imaging techniques. It's really quite useful in technology. Of course, what we'll be very interested in here is actually the electromagnetic interaction between the dipole moment of the neutron and the dipole moment of the electron. And it really is nothing but that. It's just all of what you know from electromagnetism. We can write down the interaction between the electron, between the field generated by the electron and the dipole moment of the neutron, and that will give rise to a particular potential energy. Now, what I'd like to illustrate here is that we can actually have kind of a neutron optics way of describing the interaction between the neutron and materials. And this will contrast to most of the rest of the lecture, where we are thinking about the atomic scale behavior of the interaction. But here I'm wanting to think about a situation where the sort of the atomic scale properties are not important, but I'm thinking about the average over a very long length scale in the material. So I'm describing the material not as a collection of point objects interacting with neutron, but some sort of smeared version of the potential. Just like you do in electromagnetism, where you sort of smear out to the characteristic length scale that's relevant to the problem. And the problem I wanted to look at here is that of total external reflection from a material as the neutron impinges on that material. And this is actually something you can really do in reality. You can have a neutron beam, and it can literally just bounce off a solid. It could bounce off this floor, for example, here. So it has kind of the ability of having total external reflection. So it's sort of some sort of opposite of with light. With light, we always have total internal reflection. So you're under the pool, and you can have reflection from the surface as you transition from the optically dense material to the air. Here it's the other way around, actually. And the way it works is that it's actually quite natural that the neutron doesn't really like to enter into the material. And this is expressed in the nature of the Fermi soda potential. Remember, I had 2 pi h bar squared over m times b, and then a delta function, which was my soda potential. When I'm smearing things out over a long length scale, I replace the delta function by just the nuclear density, how many per volume unit. So this just becomes, instead of a delta function, it's just number per volume unit. And this becomes overall, because a B tends to be positive. Not always. There are certain elements where B is negative, but mostly it's a positive number. That means that neutrons actually don't like to get into materials. And so when if I have a neutron with a certain amount of kinetic energy trying to traverse the interface to a solid, it'll actually have to give up some of its kinetic energy in the process of doing that. And that means that the length of its wave vector will have to decrease. Its momentum will have to decrease, actually, as it enters the solid. And for that reason, I end up with an index of refraction, because the wave vector changes its length, just like is the case for optics. But the index of refraction for neutrons is actually a little bit less than 1, as you can see in this expression. Because of this being a positive number, the potential, then I end up with n being slightly less than 1. So it means that when I enter into the solid, then the length of the wave vector actually shrinks a little bit. Remember, with optics, when I go into the solid, the length of the wave vector actually gets a little bit longer. So that means that in order to satisfy the boundary condition, then the angle of incidence, if I define it as this angle, will have to be a little smaller for the refracted beam. And this allows for this possibility of total external reflection. Okay, so what I'd like to illustrate here is that you can actually use this method to create a polarized neutron beam. And you can see it in this expression, because this is the term coming from the strong nuclear force. But then, because of the interaction between the neutron spin and the magnetization, that also represents a change in the potential energy associated with the neutron as it enters the solid. And depending on whether the neutron is polarized parallel or anti-parallel to the magnetization of the solid, then I'll either have a positive or a negative sign here. And that will influence the index of refraction. And that means that I can I'll have a different angle of total external reflection for the 2 different spin states of the neutron. And it means that I'm able to, with a magnetized material, I'm able to set up a situation where one spin state will actually have total external reflection, and the other spin state will refract into the material, and I can arrange for that spin state to get lost. So it's just to kind of get you going for this idea that I have potential energies associated with the interaction between the neutron and the solid. And this is kind of the geometric optics description. And next we're going to go into the situation where we're interested in the interference phenomena associated with the interaction of the neutrons with a solid, that is when the wavelength of the neutron becomes relevant on the scale of the atomic spacing. So here I'm taking quite a jump because I don't want to go through all of the derivation of diffraction and so on. So I'm jumping straight into reporting the expression for the differential scattering cross-section that we defined previously, associated with the dipole-dipole interaction between the neutron and atoms that are sitting inside my solid. So I'm thinking about a solid where I actually have a time-averaged dipole moment on every side of the lattice. And the lattice is indexed by L. The way you can sort of roughly think about this is that one neutron comes into the solid, and it is a plane wave state, and it interacts through the dipole-dipole interaction with all of these centers of dipole moments and creates a little spherical wave emanating from each of those sites. And to calculate then, to sort of reconstruct in the far field the intensity of neutron scattering, I have to carry out this double summation to pick up these interference phenomena where I have a phase factor that takes care of the plane wave character of the S-wave scattering from that site, and then I have the strengths of scattering from each site associated with this expectation value of the dipole moment. So the centerpiece of this expression is this essentially a Fourier transform of the spin configuration, we could call it. And so that's somehow going to be reflected in the in the differential scattering cross-section. Now, if furthermore we have a periodic magnetic structure, that means that this one is periodic as we go through the lattice, then this this differential scattering cross-section can only be finite when the wave vector transfer in the process of scattering matches a reciprocal lattice vector of the magnet. So this is not of the chemical structure, but it's of the magnetic structure itself will have some Bravais lattice associated with it if I have a periodic magnetic structure. So this is the kind of the guiding expression that we would use to try to determine the spin configuration inside a magnetically ordered material. Now there are a couple of other things that have shown up in the expression that I just wanted to emphasize. There is this prefactor here, which is basically the overall scale of the cross-section. Remember I said that this was going to have the form of an area. This is going to be in the form of an area. So this one gives the dimension of area, and the rest of it is actually dimensionless, because this one is has length to the third power, and this one has also length to the third power. So the rest of it is dimensionless, and all of the dimension is carried by this fundamental constant. So here's the volume of the magnetic unit cell, the number of magnetic unit cells, and here is a structure factor which reveals the magnetic configuration within the unit cell. So the thing that we actually are sensitive to is this structure factor, which is it's actually a vector structure factor, which involves the spin vector and then with this phase factor added up over the unit cell. And you'll see that there's a certain connection to the direction of wave vector transfer that shows up here. And this actually is a consequence of the particular form of the dipole-dipole interaction, and it implies that what we are sensitive to is in fact the dipole moment projected onto the normal plane of wave vector transfer. So anything which is any dipole moment which is pointing along wave vector transfer, I just don't see it at all. I can only see the stuff which is perpendicular to wave vector transfer. Okay, all right, so that's the elastic scattering cross-section that we use to determine a static magnetic structure in a solid. Is there any questions that you would have so far? How's the pace? Is it too wild? It's okay. Just let me know. Okay, we'll see. Just, yeah, this is your chance to ask. But you can ask later as well. Let me then go on to talk about the inelastic scattering. Okay, so, I should say this, okay, so let me just do a little bit about the geometry of the scattering process. So this is this is the elastic scattering process. I have an incident neutron beam characterized by wave vector ki, diffracted beam characterized by kf, and I can describe this as a scattering process that has this particular wave vector transfer to the sample. So momentum transfer to the sample is h bar times this entity here, ki minus kf. And it's interesting to maybe look at the length of this wave vector. So here I slid this vector back, and I have now let's see, isosceles triangle here, and I could if I describe this 2 theta as the scattering angle, it's a little weird, but for people doing scattering, it's always 2 theta. That's the scattering angle, and you can sort of split up. This is 2 theta, so there's theta and theta, k sine theta, k sine theta. So the length of this wave vector transfer is 2 times k times sine theta. And what we said in our expression for the scattering cross-section was that I could only have scattering when wave vector matched a reciprocal lattice vector of the magnetic material, in this case tau m. Now that will have to do with, that will be related to 2 pi divided by a periodicity length scale in the magnet, so 2 pi over d. Using this expression, ki kf is equals to 2 pi of lambda, I get the maybe more familiar expression for the condition for Bragg diffraction. Lambda is 2d sine theta. But I want you to remember that it's really a vector condition. It's the wave vector transfer has to match, as a vector, has to match the reciprocal lattice vector of the magnetic crystal itself. Okay, so next sorry, one more thing I needed to mention, which is that in the expression for the scattering cross section, see where's my, sorry, I was trying to find my, here, sorry. In my expression for the scattering cross section, which was here, we had down here actually another Q-dependent function that I didn't really mention. That's the atomic form factor. This is familiar perhaps if you know about X-ray scattering, that there's a form factor having to do with the spatial extent of the charge density. In this case, since we are interacting with the spin density, then we become sensitive to the spatial extent of the spin density around the atom. If it really extends a lot, then I have a very broad feature in real space that gives a very sharp feature in reciprocal space. So that will cause the scattering cross-section to exist only at very low Q. So I have some sensitivity to the extent of the spin density around the atom itself through this form factor. And here's just to give an example, this is the expression for the form factor, simply a Fourier transform of the electron density. And since the electron density for a magnetic atom in a solid would typically not be isotropic, it's going to have some shape which has to do with the orbital angular momentum state, then this form factor would also in general be anisotropic. And here's the case for copper in the m equals to 2 orbital angular momentum state. Then depending on whether I have wave vector transfer along the quantization direction or perpendicular to it, I will get a sharper cutoff when I am perpendicular to the z direction. This is the one here. Then I'll have a sharper cutoff. It looks as if it's been switched. I would like to have a sharper cutoff for wave vector along this direction. If this is the state I'm looking at, then I should have a sharper cutoff in momentum space for this direction. Oh, sorry. This is already in reciprocal space. Sorry, I thought this was real space. This is reciprocal space of the form factor itself, and so I can actually learn something about the distribution of the spin density around the atom itself. Okay, so next I want to say a few words about inelastic scattering. And so now the scattering triangle looks like this. I have my incident wave vector ki, and the scattered wave vector may now be different in length from the incident wave vector because I'm transferring energy to the sample. So I have less momentum when I come out, or maybe I have more momentum depending on whether I transferred or received energy from the sample. So I talk about the energy transfer and the momentum transfer to the sample. And just a couple of things to say about the relation between these. In principle, I could control each of these, but you can see that there's kind of a spare choice that I can make. I can choose, let's say, my incident energy once and for all, and then I could I could worry about measuring as a function of energy transfer by looking at neutrons that came out at an energy of EF. But the actual choice of the fixed EI, or possibly in some cases we fix EF, that choice actually influences very much how the experiment itself is going to function kind of at a technical level. And it also influenced the parts of momentum energy space that I can access. And just to put some formulas onto this, if I look at this scattering triangle, for the inelastic case, this is no longer an isosceles triangle, but kind of a general triangle. So with the cosine relations, I can write down the length of the wave vector transfer, and it takes this form. And you can readily see that wave vector transfer needs to be less than Ki plus Kf. That would be what I would get if I do just direct backscattering. And if I do just direct forward scattering, then I get the smallest possible value of Q, which would be Ki minus Kf, absolute value of that. So I have kind of a limited range of wave vector transfer that I can access for a given choice of either EI or EF. So these are things that we worry about when we are designing our experiments. In particular, when we're looking at magnetic system, it's often very important to be looking very, very close to Q equals to 0. Now, this becomes very difficult when you are looking at high energy transfer, because then Ki is going to be very different from Kf, and then I'm really limited to, I have to be operating for wave vector transfer larger than the difference between those two. This tends to push me towards larger values of either incident or final energy to actually what we call close the scattering triangle. Now, these things don't really come in so much when we're talking about inelastic X-ray scattering, for example, which is a technique I think you'll hear about from Radu on Friday. Because in that case, the energy is very, very high, so I'm not really changing the length of the wave vector, or I'm not changing the momentum of the photon very much as I transfer a solid state energy scale to or from the material. But for neutrons, it's really quite a significant component. Okay, so here's the inelastic magnetic scattering cross-section. Now it's the partial differential scattering cross-section, which also is it's very picky. It picks out a certain solid angle and a certain range of final energies. And the important part of the expression is this so-called dynamic structure factor, or scattering law. There's stuff in front that I might say a few words about, but fundamentally we're measuring this space and time Fourier transform of a two-point correlation function. And we get quite used to thinking about this entity, and I want to just give you a couple of examples of expressions that are quite useful as we look at the inelastic neutron scattering data. So one thing that's useful is the so-called detail balance expression, which relates S of Q omega for positive and negative energy transfer. Essentially, if you've measured it at positive energy transfer and you know that the sample is in thermal equilibrium, then you can actually predict what it'll look like at negative energy transfer. So there's nothing new in a sense by looking at negative energy compared to positive energy if the sample is in thermal equilibrium. Another thing that's quite useful is the so-called total moment sum rule, and this is really a kind of a mathematical result from Fourier's theorems, which say that if I completely integrate over all momentum transfer and all energy transfer, then in fact what I'm getting is information about the equal time and equal position correlation function. So in this case, integrating over Q, that means that I'm relating to the equal to a specific location in real space. Integrating over energy, it's a specific time. So that means that I'm just doing the expectation value with the dot product with that same spin with itself at the same time. So that's just going to be S times S plus 1, the total moment of the spin. So this, for me, is a really useful kind of idea to keep in mind, that if I have a certain amount of magnetic atoms in the solid, there's a certain amount of magnetic scattering from this solid. And all that happens as I change temperature is that the intensity kind of moves around in energy momentum space. So if I'm at very, very high temperatures, it may be very spread out in momentum space and maybe residing mostly at low energies. And then as I cool down and I get into an ordered state, I might develop some sort of dispersion relation for spin waves, etc. But I'm never losing or gaining the overall scattering. It just kind of moves around in Q energy space. The other feature I wanted to mention is that I have something we call the equal time correlation function, which relates to the energy integral of the correlation function. So if I integrate over all energy transfer, then I'm measuring in some sense a snapshot of the spin configuration, but Fourier transformed. So sometimes we use that expression. We can look at this in the notes later, but I want to emphasize the fluctuation dissipation theorem. I'm sure you're familiar with that. And if not, then this is a good time to look at that a bit, which is that that's actually a relation between the two-point correlation function and the dissipated part of the generalized spin susceptibility. So you can think of the neutron experiment as some sort of fancy version of a susceptibility measurement, but we're doing it as a function of energy at the milli-electron volt scale and wave vector transfer at the within the Brillouin zone. So it's kind of a more complete measurement, but in fact we are able to relate what is measured with neutron scattering directly to what is measured in a normal susceptibility measurement, even down to the units and everything. So that's the fluctuation dissipation theorem. This is, yes? Yeah. Yes? This more. Oh, the other way, okay. Yes? This one? This thing? Okay, so this is kind of the encapsulation of the relevant information that we get from scattering. And so here's the thing that we measure. And so if you just forget about this for now. So it's this we can talk about later, but this is kind of the key part of it. So it's a function of wave vector transfer and energy transfer. And wave vector transfer is just the difference between incident wave vector and scattered wave vector, and energy is the transfer difference between incident and scattered energy. So this function really encodes the entire information about how the neutrons are scattered from the sample. And the reason that we're interested in inelastic neutron scattering is because the thing that we can measure, which is the partial differential cross-section, it relates very directly to this two-point spin-spin correlation function. So this is really a cool thing to be able to measure because it's also kind of a central part of the theoretical description of magnetism, in fact. So you could think of this as a Green's function. And so in a sense, we're directly measuring the Green's function as a function of momentum and energy transfer. So that's okay. And the other things, I could say a few words about the other things. Here's the form factor again. And it's just because, the spin density of each atom is not really like a delta function. It's a little bit spread out in space. And it gives kind of an envelope that truncates the scattering cross-section. A very, very high momentum transfer. It eventually gets cut off by this form factor. And this is the Debye-Waller factor. That has to do with the atoms that are jiggling around a little bit, and that will further broaden the distribution in real space of the spin density, and it further kind of truncates the scattering cross-section. And this thing here is how we relate the tensor as alpha beta to the scalar, which is the scattering cross-section. And it turns out that we have this particular weighting of the tensor, and it once again is expressing this projection of the spin density onto the normal plane of scattering, which I mentioned a little bit previously, and it is a consequence of the dipole-dipole interaction that I have this particular form to it. And as you use this as an experimentalist, you actually utilize this factor to kind of tease out information about the spin space anisotropy of your system. So is it an Ising system or a Heisenberg system, etc.? That will be revealed in the momentum dependence, in the kind of the orientational dependence of the scattering cross-section. So it becomes pretty kind of involved, but I think I'll get to some examples of how we do this. But to be honest, you probably have to gradually, by doing experiments, kind of get familiar with it.
So a priori, this type of Q is known, and this exponential with this WQ is also known?
Yeah, so this thing would typically be, I should say that it really eventually will vary from experiment to experiment, but in many cases, when we're doing kind of quantum magnetism, we are aware of the atomic scale nature of the spin itself, and we would consider that to be known, if you will, and we would have tabulated information about this form factor. But there will be cases when we turn it around and we say, hey, something is looking a bit strange, and maybe the spin density is kind of leaked onto the oxygen atoms in a copper oxide. And then I would actually use this measurement of the scattering cross-section to learn something about the form factor. But for now, you could think of this one as well known. And also this thing here, the Debye-Waller factor, it could also be considered, in many cases, quite well known, because it relates to the thermal distribution of positions of a given atom, and this would be known from the structural information of the solid. So yeah, so typically all of this is kind of known, and then you try to use the scattering cross-section to eke out information about this two-point correlation function.
Okay, so how would you then go about it if this structural factor is, or see something that the structural factor is being a bit strange or something?
Oh, this form factor?
Yeah, so like you think you know it, you measure something, and you get something that doesn't quite agree with what you expect. So how do you then disentangle that it is either from this form factor or from your correlation function?
Yeah, that's a very tricky thing actually, and it's not always obvious at all. And probably you would need a specific case to see how you would go about doing this. But let me just give one example. Let's say that I have, let's say, for example, a spin ice material. We spoke about holmium titanate in the morning, and I became concerned about the form factor for the holmium, for example. So I'd been doing measurement of the scattering cross-section, and then I'm unclear as to which one belongs where. What I could do is I could replace all but one of the holmium atoms with lanthanum or something like that, so I had a very, very low density of holmium in the solid. At that point, I would be able to forget about the inter-site correlations because they were so far from each other, and I would be just scattering from individual spins. And then I could claim that what I'm measuring really is the form factor of the individual atom. That's an example. But in reality, it's not completely clear-cut, and it's naturally so because the separation that I've tried to make between the correlations between sites and the character of the individual sites is actually a little artificial because fundamentally I simply have electrons in a solid, and then I've sort of tried to pack them into a spin-like local degree of freedom that correlates with the neighboring site, and I've tried to kind of separate by energy scales the atomic physics from the inter-site physics, but it's not always possible to do that. Okay, so that's the little bit about those wonderful expressions. But I would say that over time you get used to these things, and one shouldn't be intimidated. Just come to the instruments and see how it goes, and then gradually you get into it. Now the intensity challenge, that's a bit of a problem. So you really typically would need a big crystal, and what I'd say is that I've worked on crystals that go all the way from 1 milligram, at least 10 milligram, up to really 20 grams or something like that. And we can work with the full range, but when we have a really big crystal, maybe not quite as big as that one, that we can do all sorts of magic. I mean, it becomes really very interesting because you have full access to all of these wonderful parts of the scattering cross-section. But when we only have 10 milligram, if it's a really interesting physics problem, we'll still do the experiment, but we can only, there are only certain things that we can actually say from it. So we're always working to try to get more intensity, and you could say, why is it such a problem with the intensity? And basically, the thing that we're struggling against is that with each neutron comes a certain amount of thermal energy, because they are basically trapped in nuclei, and somehow they have to be released in order to create a beam of free neutrons. The neutron only lives for 15 minutes approximately. So I'm going to, in the process of making my neutron beam, if I'm going to want millions of neutrons per second or billions of neutrons per second, I'm going to be dissipating megawatts of energy. So it's not like a laser, where I'm able to achieve these enormously high fluxes just with a battery. With a neutron source, I'm talking about having a reactor or a proton accelerator in where I will be dissipating these kind of megawatt levels of energy. And in this case, we're not interested in using this energy. We're interested in using the neutrons. But we have to, at the same time, there will always be a cooling tower dispensing with megawatts of energy, etc. And there's some sort of limit for how much power you can actually handle. And also, eventually, there's a limit in terms of the radiation damage that is accumulated in the materials that surround the reactor. So really, there's some sort of limit to how far you can go. And this is kind of the growth over time of the available thermal neutron flux that you can get with reactor sources, and then with spallation neutron sources. And I think I probably won't go into too much detail about all the nuclear engineering part of it, but here's a layout of the NIST reactor where I do a lot of my experiments. It's a 20 megawatt heavy water reactor, so that's a lot of energy. We're doing experiments at milli-electron volts. But that's the thermal power of this thing. And then there are many beam tubes that have been introduced so that neutrons can emanate from these tubes and get out to our experiments where we then are doing our quantum magnetism and other things. Here's a view of the same facilities. This is the reactor, and then you can see some instruments are immediately surrounding the reactor, and some instruments are way out at a great distance from the reactor. And you could ask, well, how do they get the neutrons to go that far without somehow getting lost? In fact, out here, the solid angle that I'm subtending to the reactor is extremely small. And the only reason that it works is because I can use total external reflection of neutrons. So actually, there are kind of waveguides, kind of like optical guides, but they work in such a way that it's basically a rectangular tube, and the neutrons are just moving along this tube, bouncing off the walls, coming all the way out to these instruments. So it's kind of artificially transport the source point to much closer to my sample. And this is great because you have lower intensity. You have lower background, and you also have more space to do all your instrumentation.
Yeah. What kind of materials are used to make the waveguides?
That's basically okay. So the considerations is that they have to be able to stand up under the radiation fields when you're close to the reactor. And then they have to have a large scattering length so that I have a big step in my potential energy function so that the neutrons don't actually enter into the material but just bounce off it. And it turns out that nickel is a material with a very large scattering cross-section. And I can actually use isotopic nickel to reduce something called incoherent scattering. So it's typically glass coated with materials such as nickel to be able to have total external reflection over this whole length. And actually, advances in these waveguides have dramatically increased the performance of these kinds of facilities. All sorts of tricks are now being done in order to extract the largest possible solid angle from the source and basically image it onto the sample position here. And I should say that these will be evacuated waveguides to reduce the scattering losses. This is the so this was all a reactor facility. This is a spallation source at Oak Ridge National Lab. It consists of a proton accelerator and then a target station. And protons impinge on liquid mercury, actually, and you create a pulsed neutron beam. And that's the particular advantage of this kind of source, is that you can control the time structure of the proton beam, and this is then sort of implanted in the neutron beam. So you get a pulsed, very intense pulsed neutron beam. And this, you can make advantage of that in your experiments. And all of the instruments are kind of sitting in this hole. And here's a picture of all of the many, many instruments that surround it, doing all sorts of different things. Fundamentally doing measurements of the scattering cross-section that I showed you, but in different regimes of momentum and energy space. And so we like to use, a couple of the instruments up here. This instrument I like to use, and so on. And so you'll come to this facility for maybe a week or so and do your experiment, and then go back and kind of analyze your data. Now, the instrumentation has developed a lot over the years. Here's Scholl and Woolen, I think it is, at Oak Ridge Lab, trying to use neutrons to measure the structure of materials. Now there's just a whole range of different instruments doing the same thing, essentially, but much more efficiently and kind of optimized for different parts of the challenge. Likewise, for the inelastic scattering, here's Bert Brockhaus in Canada, actually, doing an experiment on a triple-axis machine, and here's just a whole bunch of different instruments. These are mostly at Oak Ridge, but also at NIST. We can now probe energy transfer all the way from microelectron volts to electron volts using this kind of method. Okay. Oh, I should say finally that these facilities are available for users. There are also facilities in Europe, various facilities actually in Grenoble, in Rutherford Lab, and there's a new facility being built in Sweden. There are facilities in Japan, in China. These are generally available for users, and you can certainly apply for beam time at these kinds of facilities. And there's typically, even though there's some kind of limitations, but in fact, I think not at these facilities. So just submit your proposals, and it's kind of a competitive process for those with good ideas for experiments. I think that's my neutron introduction. I hope it was not too heavy, but it was quite different from what you'd heard, at least thus far. So if there are any questions, please go ahead. Otherwise, let's see, how am I doing for time? I spent an hour. It's a little much, but probably we'll only get to here, but that's fine. So now I'd like to use this method to probe local moments in insulators. And actually, these are pretty brief sections, but I just want to say a few words about this topic. So, as I said, I'm going to be thinking about electrical insulators, and I want to describe the magnetism as arising from local moments that are somehow interacting with each other. And these could be associated with 3D, 4D, 5D, 4F, or 5F electrons. We have magnetic materials based on all of these things. And in terms of the factors that determine the nature of the spin, then certainly their intraatomic Coulomb repulsion is going to be significant. There is the impacts of being inside a crystalline solid will create an anisotropic crystalline electric field. And then finally, I'll have spin-orbit coupling that will link the orbital angular momentum to the spin angular momentum. And these effects will have different strength as you go across the series. Generally, the spin-orbit interaction will increase in significance as we come to heavier and heavier elements, and the crystal field term will tend to become more, less important as I come to, let's say, 4F electrons particularly. In that case, the spin-orbit interaction is really dominant, and the crystal field interaction is just the final decoration, because the 4F electrons are kind of buried inside the atom itself. For 3D electrons, on the other hand, the crystal field interaction is stronger than the spin-orbit interaction, and so in that case, I'll deal with this one last in my perturbation series. So let me give you an example of an experiment that probes the impacts of crystal field excitations in a material. It doesn't matter so much in this case, the particular structure. This turns out to be a Kagame-related material. The magnetic ion is neodymium in this case. It has it's a Kramer's ion, so it has a spin-orbital angular momentum quantum number of 9.5, so J is equals to 9.5. The spin-orbit coupling is really strong, and it creates this J equals to 9.5 multiplet. There will be excited multiplets as well, but most of the interesting physics will be operating in the lowest energy J multiplet. And then crystal field interactions will, or the crystal field will be anisotropic, and it's going to lift that tenfold degenerate state. Because it's a Kramer's ion, I can only get down to doublets. I have to actually break time reversal symmetry by having some sort of ordered state or applying a magnetic field to lift that degeneracy. So I'm going to have, in a low symmetry environment as I have in this ion, I'm going to have actually 5 doublets in the system. Of course, one of those doublets is going to be the ground state, and then I'm going to have 4 excited doublets. And so if you look to the far right, you'll see actually that I have, well, what is shown here, what's shown is intensity as a function of energy transfer and momentum transfer. And you can see these kind of lines that are just horizontal lines as a function of momentum. Now, they correspond to crystal field excitations, and I have in this case 1, 2, 3, 4 crystal field excitations going from the ground state doublet to the 4 excited doublets. And you can see a couple of things here. The intensity is decreasing as a function of wave vector transfer, and that is because of the form factor. So the 4f electron spin density is distributed. It has some spatial extent, and it falls off, and the way that it falls off is actually consistent with the kind of tabulated form factor, the 4f electron spin density. What else? Well, there's no dispersion. You don't see this thing kind of wiggling up and down. And this is because the interactions between these 4f electrons are really very, very weak. They are on the scale of maybe several Kelvin or so, and so they don't actually show up here. There's no kind of dispersion that I see at all in these excitations. So I simply have 4 excitations, and what I'm showing you here is actually measurements at 3 different values of the incident energy of the neutrons: 150 millivolts, 80 millivolts, and 40 millielectron volts. You can say, well, why did you do that? And the reason is that when you go to lower values of EI, you get better energy resolution. And so actually this gives you the complete overview of the whole thing. And I see an excitation at 120 millielectron volts or so. Then to get better resolution for lower energy, I went to 80. Now I can't excite this thing anymore because I can't lose more than I have. You know, the most I can lose is 80 millivolt, then the neutron just stops. So I can't see this excitation anymore, but these other ones are quite nicely split out. And then finally down here at 40, I see just the 2 lowest energy excitations. And one thing you notice is that the lowest energy excitation is just below 20 millielectron volts. That's really a huge energy scale. That's 200 Kelvin for a system which has collective physics in the kind of Kelvin energy range. So for all of the thinking about quantum magnetism, it's all really to be projected onto the ground state Kramer's doublet. I don't need to really worry about this excited doublet to describe the low energy physics. So from these kinds of measurements, we actually know, we know the whole expression for the scattering cross-section. We know how to write down the crystal field Hamiltonian, which would be too much to really describe that, but there are just several parameters in that Hamiltonian that we can actually determine by this kind of measurement. So the way we would do that is to fit the spectra. So this is intensity as a function of energy. So we can both deal with the position of the peaks as well as the relative intensity of the peaks. And from all of that, we can fully determine the crystal field Hamiltonian. And from that, we can actually calculate the susceptibility as a function of temperature. In this case, we plotted inverse susceptibility versus temperature. And it takes this kind of form. And actually, the dashed line was what we calculated just directly after having determined the spin Hamiltonian. And it didn't agree so well with the data. And we just took some time before we figured out what was going on. It was actually because there was a slight deficit of rare earth of neodymium on this ladder, so there's some vacancies in there. Actually, the chemist had to eventually acknowledge that, and then when we took account of those impurities, then we could actually pretty well account for the measured susceptibility curve. And then from all of this comes out this is kind of a final fit to the ground state Kramer's doublet. So we can now resolve all of the contributions from the various elements of the j equals to 9½ multiplet. So you can really, using this method, determine the wave function associated with the individual spin in the system, and then you can go on from there to do your collective physics. Good. So that's the rare earth case, so 4f electrons. Just wanted to say about the 3D electrons, and this links to the lecture by Giovanni on the day one when I was here, talking about the metal insulator transition. To describe 3D electrons, we would start with a Hubbard model with a hopping term and a on-site repulsion. And in these materials, we're going to think about the case where U is extremely large, which localizes the charge, but that leaves behind degeneracy in the spin sector, which can be described by this effective Hamiltonian. It projects out all of the dynamics onto just the spin degree of freedom, and then so it becomes of the form of a Heisenberg interaction with a certain exchange constant that's related to t squared over U. Let's see, I think I have an example of a measurement now of spin wave excitations in a particular compound, which is actually conducting, and we're looking at it in a different context, but it was just a recent experiment we did that was kind of neat. So this shows the measurement of neutron scattering as a function of energy and momentum transfer. And you see, this is a material that has long-range antiferromagnetic order. This is the transition metal ion. And it has antiferromagnetic planes stacked on top of each other. And what we see is this inelastic scattering. We only see the inelastic scattering along sharp lines through momentum energy space. You can see it all the way down here and then it comes back up again and down here. So gamma point, that's the wave vector point that corresponds to this structure because the chemical and magnetic cell, unit cell actually match each other. So the lowest energy excitation corresponds to creating a spin wave that will cause the spin to deviate from its preferred easy axis direction. That's why I have a gap in the excitation spectrum. And then as I increase momentum transfer away from the gamma point, the energy correspondingly increases. Interestingly, in this case, there's kind of a dip again, and I almost come down to a soft point again at the M point in the zone. That's the half-half O position. That corresponds to satisfying an antiferromagnetic interaction between these two sites. So that's the J2 interaction. So the fact that the mode sort of comes down here is revealing to me that I actually have pretty strong antiferromagnetic interactions between next nearest neighbors. Apart from the near neighbor interactions that establish the ordered state, I have this kind of frustrating element in the system. And so by analyzing these kinds of data, comparing to the calculated intensity by spin wave theory, I can extract parameters in an effective Hamiltonian that its origins are the Hubbard model, but projected into spin space, and I can then basically pick out those parameters of the interacting spin model by this kind of measurement. Oh, yes? Yeah?
How do you get easy access terms from the stubble model? Because when the stubble model is Heisenberg, whereas easy access terms.
Yeah, that's actually, that was a very good question. In fact, after we wrote this, it turns out that actually you can equally well describe this kind of gap in the excitation spectrum by a single ion anisotropy term or by a exchange anisotropy term. So actually, you could have a single ion term which is something like, I could have something like a minus d S z quantity squared. This type of term could show up, which would actually favor the spins pointing in the z direction. That would, whenever I try to excite a spin wave, I have to pay the penalty of violating this condition of being along the z direction. That would open a gap in the excitation spectrum. But likewise, if I was to have a exchange term which had, let's say, j times s, sx, plus sy, and then maybe plus delta sz, sc, as I'd have to do this kind of term. So if this one was just 1, then I'd have an isotropic Heisenberg interaction. But if I let this one deviate from 1, make it a bit larger than, well, it depends on the sign of this one, make this one positive, and then make this one, I think I want to make this one a little bit less than 1, a little bit less than 1 in that case, then I can favor spins pointing along the z direction. That'll also have the effect of inducing a gap. So actually, it turns out that you can't really, I don't really know how to distinguish the D term from the exchange anisotropy. They always have to be there at the same time, and it's really difficult to separate them out experimentally. Of course, for the case of spin 1/2, we can't have, this type of term is not going to be relevant in that case. But for integer spin, it will be relevant. Now, all of these things eventually have their origin in spin-orbit interaction. But the way I'm presenting this and the way people usually proceed is that their interest is the collective physics, and so the task that we're undertaking is to determine an effective kind of low-energy spin Hamiltonian. Sometimes there's less interest in the particular nature of these terms in simply knowing them and then exploring the collective physics that arises out of that. Okay. So that's the example of spin wave excitations. Then I want to give another example of kind of a simple form of excitations that we can have. And that is the case of, so that's the case of a valence bond crystal. Okay, so this relates to Lucille's talk. She was talking about some form of a resonating valence bond state where every spin is forming a singlet, but which spin it forms the singlet with is changing all the time. And so you have this massively entangled superposition of singlet coverings of the lattice. But in a valence bond crystal, you have a specific singlet covering, so that this spin is always forming a singlet with this spin. And you've somehow broken the symmetry. Either the valence bond formation actually caused the symmetry to break, or maybe it was already broken from the beginning, and then these singlets just naturally fall into place as you cool down the system. So that kind of material has very different excitations than what Lucille was talking about, because in that case the spinons cannot move apart. Actually, once you create a triplet from a singlet, then this pair of spinons, if you will, they have to just stay together, and so they can now move around by hopping through this lattice. And so that kind of system is not going to exhibit the features of fractionalization. It actually looks a lot like a long-range ordered magnet, and this kind of excitation, I think many people would still call it a magnon. It's a little weird because it lives in a system that doesn't have spin order, right? There's no spin has an expectation value in the system. It's in a quantum fluctuating state. And so there's actually no elastic scattering at all, no magnetic Bragg peaks, no elastic magnetic scattering. All of it is inelastic, and yet we describe it as a valence bond crystal. So it's not actually a very particularly interesting thing in a sense. And so what the excitations look like, this is a material that actually has kind of a symmetry broken state from the very beginning. It really consists just of pairs of spin half degrees of freedom, and these form singlets, and there's a triplet excitation that you can undertake. The susceptibility just looks like this. Initially it looks like as if it's going to be like a Curie-Weiss law or something that might eventually develop magnetic order, but because of the kind of dimerization of the material, then eventually the susceptibility just rolls around and it has exponentially activated behavior at low energies. And what we see in neutron scattering is this dispersive mode that just meanders through a reciprocal space. All of it is resolution limited, and the dispersion comes about because of the ability of or indicates the ability of this triplet to actually hop through the lattice. And so that's the other type of magnon excitation that we can associate with a valence bond crystal state. Good. So as anticipated, I'm not quite basically reached this stage here, and I have about 15 minutes left. So I guess I could break here, or I could go on a little bit, depending on how many questions. Let's take a couple of questions, see how it goes. Yeah. Of the neutron? Oh, okay, yeah. Yes. Okay, so let me just kind of go. I think I just want to go to maybe this kind of thing. So this is the basic character of the experiment, but the question is, how do I actually pick the initial energy? So, if we so there are various different ways that we do this, and we can talk about it for a long time, and I really like the topic. But to give specific examples, at a reactor-based neutron source, then we have basically a continuous beam of neutrons coming from the source. And this is actually a Boltzmann distribution of neutrons, so it's a fusion source, essentially. And so the first thing we do is that we ask ourselves, what energy of neutrons would I like to use? Well, I think I'd like to match the neutron energy sort of to the energy scale of the system that I'm looking at. So if I'm doing low temperature physics, I should use low temperature neutrons. So we actually use neutrons that are equilibrated to hydrogen, liquid hydrogen at 25 Kelvin or so. So it's a really quite cold gas of neutrons that's coming out. But this is really a gas of neutrons, with wavelengths spanning from 10 angstrom to 2 angstrom. So I need to pick out a specific wavelength. And the way I do that is typically by diffraction. So I just use, I use a crystal, and I'll have my source of neutrons here, and then I'll have a single crystal here, and I'll have some sort of way of controlling. This is a source that goes in all directions, but I want to set up some sort of system so that I'm only picking out the neutrons within some particular solid angle, so that they can interact with the crystal. And then this crystal will be set up so that I have a specific reciprocal lattice vector of the monochromator, and then I have that, in order to have diffraction, then this condition has to be satisfied. So from that I get that wave vector, in order to have diffraction, must be equal to monochromator reciprocal lattice vector divided by 2 sine theta. So you can see that by changing sine theta, I can control the length of k. So then I basically arrange to have my sample sitting over here, and I vary this angle to pick up different energies. So it's actually a pretty awkward thing to do mechanically. I'll just show you an example. I think I can maybe show you. Oh, no, sorry, here. So here's it's really difficult to quite notice, but here's an instrument. It's kind of at a distance and so on, but all of this stuff has to physically move around on the floor to move the sample to different locations to get this diffraction condition. So it's kind of a weird thing, but that's the way we typically do it. Now, one little interesting tidbit is that we've heard a lot about graphene in this meeting, and we actually use graphite to reflect the neutrons, and we have for years and years and so on. And graphite is, we use something called highly oriented pyrolytic graphite, which is actually kind of a stack of graphene which is rotated at random angles. So talk about the magic angle condition. We like these particular crystals, it's not because of the magic angle, but it's because of the fact that they can rotate. And this actually creates a very large mosaic distribution in the crystal. And it again comes back to the fact that our neutron flux is quite low. So if I was to use something like a perfect silicon crystal, I would barely get any neutrons out at all. So I need to use a very mosaic crystal with a large mosaic angle so I can pick out a somewhat larger slice of phase space for reflection. So that's the one method. The other method, which is used at the spallation sources, so an instrument such as this instrument, and this instrument actually, what it does is it actually times the travel of the neutron through the system. So since the neutron is created at a specific time, then if you sit at some distance from the source, then as a function of time, you're going to first see the neutrons that are really fast, and then the stragglers will eventually come along and get to the sample. So what you can then do is to set up between the sample and the source, you set up a chopper which only kind of opens up during a short period of time corresponding to the neutrons of the particular energy that you'd like to emit. And so that's the time of flight method to select the neutrons out. So,
And the second one is also technical.
yes?
But you showed some data in the second section, which was about you were sweeping the temperature. So it was up to, I think, room temperature.
Mm-hmm.
So my question is not how you sweep the temperature. I mean, I don't mean how do you sweep temperature. I mean that are you using some devices, I don't know, like PPMS, and in this case, how do you have still your neutron flux alive?
Okay.
You are just passing through the system which is suitable for cooling down, but I mean when it just faces some wall, I
Yeah.
just feel like you will lose your flux.
Oh no, yes, that's the thing that eventually this becomes kind of second nature, you know. And to be quite honest, when I was initially a student, I was quite surprised by this, you know, because I was looking at my samples inside a cryostat. There was aluminum and all sorts of stuff, and you know, but you know, the neutrons happily pass through. Literally, a meter of aluminum is okay. A meter, just you know, it's depending on particular which material you're looking at, but you can easily pass through a lot of material without very much scattering at all. So, you know, this is a little bit exaggerated. So we do quite an effort to actually reduce the amount of extraneous material that we pass through, but it's not a problem, let's say, for a cryostat. We can have, you know, an external shield and some thermal shield, and we can use a dilution refrigerator in a vacuum chamber and all these things. We can use a magnet, and we can pass through structural material to get into the magnet. So this is one of the advantages of the neutron method, that in fact we can really pass through significant material in the process of getting to the sample.
And what about deviation of the beam?
Oh, it's still fine. You know, there certainly are some problems that we worry about in the finer details of it, but you know, to just get a sense of it, the typical amount of scattering, initially I talked about the overall scattering cross-section, and typically for you know, some sort of crystalline solid, I would only scatter maybe overall maybe 5 or 10% of the neutrons would actually scatter. The rest of them would just pass straight through. So if I'm talking about a shield around a cryostat made of aluminum, then we may only lose 2% or 3% of the neutrons in the process. The rest of it just passes through. Now those 2 or 3% of the neutrons could give you quite a headache actually, because they may scatter, you know, various things can happen that they could become a background for your measurement. Yeah, and that certainly is a concern, but it's a lot easier than actually, I mean, at least in my impression, compared to you know, resonant X-ray methods that require, you know, pretty thin windows and really evacuated beam paths and so on. It's actually pretty forgiving. Yes. So other questions? Yes? Detailed balance. A detailed balance. Okay. So let's just let's go back here and take a look at our expression. The detailed balance. Okay. What could we say about detail balance? Okay. All right. So let me just maybe I'll just raise this thing up. So I won't. Oh, okay. Okay, so this is my dynamic correlation function, or my scattering cross-section. as a function of energy transfer, and this is 0 energy transfer. And what the expression for detailed balance says is that S minus omega is equals to e to the minus beta omega S of omega. So let's think about what happens if I go to, let's say, very, very high temperatures first. Okay, so I'm going to go to T, don't worry too much about the units, but I'll go to T much, much greater than omega. Okay, so that means that this factor is essentially it's just going to be 1. There we go. So this factor is going to be just 1, and then S minus omega is just going to be equals to omega. So I'm going to have, if I have an excitation over here, for example, then I'll have the same, essentially the same intensity sitting over here. I could also have something sitting at the elastic line if you'd like, but this would be how it would look at really high temperatures. Okay, then let's try to go to, so basically T much larger than omega, it means symmetric. Now there's an interesting little wrinkle to this, which is that if I put, maybe I should do that later, but if I put Q in, then I actually need to put it in with a different sign here. Usually that doesn't matter actually, because I very often have inversion symmetry in my sample, but if I have a sample that doesn't have inversion symmetry, I have to remember that I actually change the sign of Q as well in this process. Okay, now at very high temperatures, symmetric. If I go to very, very low temperatures, much, much less than omega, then we only have intensity for omega greater than 0. So this is because S of minus omega becomes heavily attenuated by this factor here. And so whatever I have on the positive energy side is going to be much, much stronger than on the negative energy side. So if I was to try to see what happened to this system when I cool down, then I would completely get rid of this stuff over here. Ooh, the blue one. Okay, I completely get rid of this when I go cold. And this one over here can still be there. Maybe I'll have it grow up a little bit, and I also want this one to grow up a little bit. But I'm going to only be able to have intensity on the positive energy side, no intensity on the negative energy side. Now, why is that? Remember what's the way I define my sign here is that positive energy transfer means transferring energy to the sample. Negative energy transfer means that the neutron comes out with more energy than when it came in. So when the sample is really cold, I'm not able to have that kind of stimulated emission process take place. And so I'm going to lose all of the negative energy transfer processes, but I can still actually deliver energy to the sample. Now the reason that I boosted this one and this one a little bit was the total moment sum rule. I cannot lose intensity. If I lost this peak here, then I'll have to find the corresponding intensity somewhere else. So to make it balance out, I gave more intensity here and more here. Who knows what will happen in a particular case, but I should generally expect to conserve the overall intensity that's involved. Yeah, so actually, one thing we can say quite kind of generally is that when we think about quantum magnetism, we want to be looking at materials that actually where a large part of the scattering cross-section arises, at t equals to 0, arises from inelastic scattering at positive energy transfer, so that most of the intensity actually lives over here and not so much of it lives in the elastic channel. In fact, in a quantum spin liquid, we would like to not have anything in the elastic channel at all. We'd like to see only inelastic scattering. So at t equals to 0, we would just see intensity sitting in the positive energy side, nothing in the negative energy side. Yes. Any more questions?